So, in the last sessions, we discussed about response of series RLC circuit and parallel RLC circuit. And let us have a quick review on these two concepts. So, in series RLC circuit, so we found the impedance of the circuit which is equal to R plus ZL plus ZC, which we got as R plus J XL minus XC, which can be written this term into polar form as mod ZT at an angle of theta, where mod ZT is the magnitude of this impedance and theta is angle of this impedance. And apart from this, we seen one more interesting fact in the form of phasor diagram, that if we want to draw the total phasor diagram corresponding to these all quantities, which are voltage across the resistor and reactive elements voltages, which are VL and VC. So when we are finding the total voltage V by using phasor diagram, if you observe this VL and VC terms, so one is quite phase opposition to other. Like if one is at plus 90 degrees, other is at minus 90 degrees. So which will be directly straight away, so quite opposite to each other as like this. So this we call as in phase opposition. When two voltages or some any vectors are in phase opposition, when we add up these two, we get the result of this subtraction. Like if one is more than the other, then the left out term will be like higher value minus lower value. That what we had seen here. See here, VL is higher. In case VL is higher, then VL minus VC is what the red color arrow, which is the resultant or which is the addition of the voltage across the inductor and voltage across the capacitor. Now after getting the total addition of these, that is voltage across the resistor and inductor, which is the voltage of these reactive elements, let me say Vx reactive elements, then addition of this Vx with the Vr is what the total voltage. See that this red color one is what the Vx and Vx plus Vr is what the blue color one. That is phasor addition. So this vector line plus this 90 degrees vector line addition represents this blue color line, which is the resultant phasor of these two. So here one thing you should observe, that when we are taking the sum of the voltages across the reactive elements, what are the reactive elements? Inductor and capacitor. So this total voltage Vx across these elements depends on whose voltage is higher. For example, if the inductor voltage is higher, then the net resultant voltage, which is Vx, will be in the direction of VL. See this, Vx is as like in the direction of the VL. VL is upward, so Vx is also upward. In other words, if capacitor voltage is dominating, if Vc is more, then this Vx value is Vc minus VL, which is in the direction of Vc, that is in downward direction. Now Vr plus Vx is what the our total voltage V. So now in the same way, for a parallel RLC circuit, so we had found the admittance. So we had found the admittance. Admittance is represented by the letter Y. Admittance Y as G plus J BC minus BL, where G is the reciprocal of the resistance, BC is the reciprocal of capacitive reactance, BL is reciprocal of the inductive reactance, like that. So Y can be expressed as mod Y at an angle theta where mod y is square root of g square plus bc minus dl whole square, whereas theta is tan inverse of imaginary part divided by real part. And when we talk about the parallel circuit, we see everything in terms of the currents instead of voltage. Why? Because voltage across each of these elements is the same. Now, as like in the series circuit here, depends on the current, which current is dominating. Is the inductive current dominating or capacitive current dominating? And based on that, we find the net current taken by these two elements, which we call as, let us say, Ix. Ix is sum of the currents of the inductor current and capacitor current, which I can write as Ix is equal to IL plus IC bar. Now, as because IL and IC are quite in phase opposition, like when I add up these two things, it is equivalent to subtraction. Like depends on the dominant quantity, the net resultant will be in the direction of the dominant quantity. This is what the Ix. Ix will be in the direction of the capacitor current if capacitor current is higher than the inductor current. In other words, if the inductor current is dominating, the resultant current Ix will be in the direction of the inductor current direction. So, as like in the series circuit. Now, so try to observe that we had seen out of three possibilities, only two possibilities are discussed here. One is inductor current is higher than the capacitor current, or capacitor current is higher than inductor current. But there may be a situation that both currents are equal. That case we would like to discuss today. In the same way, in series circuit also, the inductor voltage may be higher than capacitor voltage, or vice versa. The third possibility is that both voltages may be equal. So let us talk about this kind of situation that when VL and VC both are equal, how much is Vx? Vx is just addition of these two things. One is in the positive direction, another is in the negative direction. When you add up these two of equal value, you will get the 0. When VL is equal to VC. In the same way, in parallel circuit, when IL is equal to IC, one is that positive direction, another is exactly in phase opposition. So when we add up such phasors, we get net is 0. So let us talk about such a condition, so which we call that condition as resonance. Resonance. Right. So if we take any circuit like AC circuit, let us assume that this is a circuit, electrical circuit. And usually the circuit consists of passive elements, passive elements, passive elements. What are they? R, L and C. And the network also consists active elements. Active elements. Active elements. So this is general circuit nature that network may consist passive and active elements like RLC and some voltage sources or current sources. Now, if we see that in this kind of circuits, usually resonance occurs, resonance occurs in certain conditions that when 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 let me say that when inside this circuit, let us say some current, so circuit current, that current, when the current goes to either maximum either maximum or minimum in the circuit, when the current goes to either maximum or minimum. So how we when we see this kind of situation that the current goes to maximum or minimum is that when inside this circuit if the frequency is varying under this condition that the current in the circuit may goes to maximum value or minimum value. So this kind of condition we call as resonance. So just in simple words we can say that resonance occurs in a network or circuit in which the circuit consists passive and active elements. So when the current in this circuit goes to maximum, either maximum or minimum for a varying frequency, And usually once the frequency is varying, at a particular frequency, we see the current will be either maximum or minimum. That corresponding frequency and that corresponding condition we call as a resonance condition. And as a result of this, if we see that, so if the current is going to maximum or minimum, we could see the impedance. Let me write in generally as like this. In these conditions, the impedance is so or the impedance becomes again. So let me say little vice versa situation that if current is going to the maximum, impedance goes to the minimum, or if the current is going through the minimum, the impedance goes to the maximum. Why? Because you can see that so the current we had written previously as voltage divided by the impedance. If current is maximum, obviously impedance is minimum. So if current is minimum, impedance is maximum. With that kind of situation, that means we can say either in terms of the current or in terms of the impedance. So this resonance situation. Now let me take the series concept, that series resonance concept, series resonance, series resonance. So for which just let me take this series RLC circuit quickly. So this series RLC circuit which we had discussed in the last session. So let me take that diagram over here and try to observe that here some of the important elements characteristics and let us understand some of the things in this. First thing is that in this series RLC circuit, I would like to focus on these reactive elements which are inductor and capacitor. Inductor and capacitor. First, what is my focus is that what will be its nature of the reactance with respect to frequency. That this can be written as 2 pi f into L. So this is what the reactance. Now as frequency varies, let us say this is frequency. Frequency is varying from 0 to maximum value. When frequency is 0, what is the value of the XL? 0 into L is what? 0. That means if frequency is 0, the XL is also 0. If frequency is increasing, the XL also increases. Why? Because frequency is directly proportional to the XL. So how does it look like? Is it look like a straight line as like this. So this is what XL versus frequency. XL versus frequency. That means if frequency increasing, XL also rising. This is for the inductor. In the same way, let us see about the capacitor. So what is capacitive reactance is Xc. How much is Xc? 1 by omega c. What is omega is? 1 by 2 pi f into c. Now for this situation, let me take the frequency again. Let us vary the frequency 0 to some maximum value. When frequency is 0, what is Xc? So Xc at f is equal to 0 is Xc is equal to 1 by 2 pi into 0 into c. 1 by 0 is infinite. That means when frequency is 0, the Xc will goes to very high. How much is high? Is that infinite value. So somewhere it goes to infinite like that. Somewhere it goes to infinite. This is corresponding to infinite. If frequency is infinite, means this side. If frequency goes to infinite, then 1 by infinite is what? Xc is equal to 0. If f is infinite, Xc is 0. See, 1 by infinite. F is infinite means 1 by 2 pi infinite into c. How much we will get is that 0. That means this goes to 0 where when frequency goes to infinite. So this is the curve corresponding to Xc versus frequency. Xc versus frequency. So these are the individual reactances, that is, see here XL and Xc. Now when I try to take together these information that as like this, if I'll take this kind of situation, that the total reactance X, which is equal to XL minus Xc, which is equal to omega L minus 1 by omega c. Now just for the sake of this, just I will try to put in the dotted line this XL and this in terms of green color. These are what? Dotted lines are what? What corresponding to XL and XC alone. So let me write here. So these dotted lines as what we had seen previously. So this is what XL versus frequency. This is what Xc versus frequency. But what I need now? XL minus Xc. XL minus Xc. Now for which? So we have to take minus Xc. So how we get the minus Xc corresponding graph? So just let me expand this downward. Just whatever you got for the green color, you take the mirror image, that is what? Minus Xc. Okay. So now just I am taking here. So if I'll move in this direction, let me take with this color. Mirror image of that is what it look like this. So let me take more precisely as like this. See. So this pink color one is what? Let me say is what? Minus Xc versus frequency. Now what I will do is that this XL, can I say this one? Total X is XL plus of minus Xc. That means negative value of the capacitive reactance is added to the inductive reactance. Okay. So just this minus Xc I am taking as XL plus of minus Xc. So XL is this one. So minus Xc is this one. Now add up these two. Add up these two. So what kind of characteristics we get? So that is what important for us. Okay. So for which, so let us take, for which let us take, so uh, 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 in general in this way that, so what I'll do is that instead of taking directly x, I'll take the magnitude of the x, mod x, just to have, again we no need to draw one more different kind of curve. Now once I'll add up, so XL, how much is XL at zero frequency? Zero frequency, here XL is 0. How much is XC? Minus infinite. So 0 plus minus infinite is minus infinite. Mod of that is what? Plus infinite. Mod of, mod of any negative value is, mod of any negative value like 10,000 is what? 10,000. Like, so 0 plus minus infinite is minus infinite, but mod of that minus infinite is what? Plus infinite. Means how it look like? It look like XC. Now let me plot carefully that, just directly, X nature as frequency is lower value, that is corresponding to 0, capacitive nature is dominating, means it goes to infinite. Next, as frequency increases, then inductive nature going to dominate at a particular value, and at a particular position, at a particular position we get, we get the minimum value of the reactance, or I should say instead of this one, just why, because see, at one location this becomes 0 when these two are equal, where, just let me identify that. So this is equal in length, this much, then same amount of the equal length can be observed here, more or less close to this. That means around this position that become, that become 0. So that means, so let me put in this way, as like this, or just let me take carefully 0, then it try to follow the inductive nature. This is what, let me write, mod x, which is equal to mod of XL minus XC. This is very important. Okay, so as a graphically, this is what the reactance of the total circuit. Now just I don't want to make much complex of this. Instead of that, what I will do is that, now let us see, let us see the total impedance of this series RLC circuit. What is the total impedance of the series RLC circuit? R plus J XL minus XC. Now, if I'll make this to be more interesting form, as like this, magnitude of the impedance is equal to square root of R square plus XL minus XC whole square, and this I can make one more interesting feature, that R square plus omega L minus 1 by omega C whole square. Now if you observe that, if omega is varying, is varying, we can see from this graph, from this graph, at a particular value of the frequency, means at this location, the XL is equal to XC. This is what XL, let me say here, this is what the XL value, this is what XC value. XL is equal to XC, but one is in opposite to other, one is positive, other is negative. As a result of this, the net reactance is 0. So when frequency is changing, clear? when frequency is changing at a particular location of the frequency, the inductive reactance XL is equal to capacitive reactance, in which the net reactance is becoming 0. So now at that location, like if omega is varying at a particular frequency, at a particular frequency, at a particular frequency, XL is equal to XC, XL is equal to XC. That implies omega L is equal to 1 by omega C. So that implies, so omega square is equal to 1 by LC and omega is equal to 1 by square root LC. And if you want, you can write this omega as 2 pi F, which is equal to 1 by square root LC. And F is equal to 1 by 2 pi square root LC. This F we call as resonance frequency. Resonance frequency. Resonance frequency, which is usually represented by F suffix R. F suffix R. So resonance frequency F suffix R is equal to 1 by 2 pi square root LC. So try to observe as what we defined the resonance as here somewhere. See here, resonance occurs when current is maximum or minimum when frequency is varying. In this condition, the impedance can be minimum or maximum. So that is what the situation we are seeing here. This is what the impedance, which is mod Z. At this frequency, let us see that at FR, XL is equal to XC, thereby the total impedance of the circuit is square root of R square plus XL minus XC whole square, which is equal to square root of simply R square plus XL is equal to XC, so this term goes 0. That means this entire thing will become simply R, which is the minimum impedance. You will not get below this level. If frequency is other than resonance frequency, then definitely this imaginary, that is reactive terms will be there. Once we add other than 0 to this any positive number, definitely that value will be higher than this value. So, but at this condition, this term completely going and vanishing to 0. So, it completely vanishes. So, that is what the minimum impedance under this condition. So, if we plot once again this total impedance curve, that is mod Z, which is equal to square root of R square plus omega L minus 1 by omega C whole square with the frequency, what we get is that as like this. Previously, we got this to be 0 for what? For only reactive part. But now additionally we are adding resistance, so that curve will jump by a value of R. This is what the R, which is minimum value. Minimum Z is R. And at what frequency we get this is FR, resonance frequency. If frequency is increasing, first the impedance is falling down. How long it will fall? To the value of R. Then after that it will rise. and it will take the nature of the inductive. See here, this is very important conclusion for many competitive exams. Just see here, for this side, for this, let me say, just this green color line, just try to observe. Towards this side, left side, it look like capacitive nature. Capacitive nature. Why? Because see that this red color line look like the nature of the XC. See here, this is what the XC versus F, green color, see here, towards this left side. Nature of this impedance is XC nature. Then after this minimum value, its nature is following the XL nature. So that's why below the resonance frequency, the circuit is dominantly capacitive in nature. Above the resonance frequency, it is inductive in nature. Inductive in nature. Then, if it is below capacitive nature, above inductive nature, what about at resonance frequency? At FR, the impedance is, the Z is pure resistive nature. Resistive nature. It is pure resistive nature. So this is one of the important point. Okay. If the frequency is below the resonance frequency, the impedance will follow the pattern of the XC, that is capacitive in nature. If it is above the resonance frequency, it follows the inductive nature, which is XL nature. But at resonance frequency, it is neither capacitive nature nor inductive nature. Instead of that, it is pure resistive nature, which is equal to R. Okay. So this is what about the resonance in a series circuit. Now just as a summary of all these things, just let me put one phasor diagram that what we had seen here in case of series circuits. So we had drawn the phasor diagram for VL greater than VC and VL less than VC. But now let us draw the phasor diagram in a simple terms for VL is equal to VC. VL is equal to VC. So let me say that at resonance, at resonance. What happened at resonance? That means frequency is equal to resonance frequency. At this resonance frequency, how much is Z? Mod Z is equal to simply resistance. You can say XL is equal to XC. If XL is equal to XC, as a result of this, VL magnitude is equal to VC magnitude. Both are same. Then if we draw the phasor diagram, if the total voltage is here, this is what the total voltage V. And if I take the VR, this is what the VR, resistor voltage. And if the capacitor voltage is here, the current is known. This is inductor voltage. If this is the inductor voltage, the capacitor voltage is in downwards but equal in length, Vc. Now if we add up these equal voltages, how much we will get? 0. So that is what, let me say here that, so the addition of, this is what Vx, let me say, so Vx is equal to VL phasor plus Vc phasor. One is 90 degree, another is at minus 90 degree. When we add up that, this becomes 0. Now 0 plus VR is what? The total voltage V. So this is not the total voltage, this is generally something. So this blue color one is what? The total voltage. That means, so we have RLC circuit in which total voltage is equal to VR plus VL plus VC, as because VL is equal to VC, these two terms are equal to 0, then 0 plus that is what VR. So total voltage is simply resistor voltage. This is what the phasor diagram for a series RLC circuit under this condition. Okay. So now just let me summarize about this resonance. So let us see some of the important points about these resonance. So the first point in this is that uh, let me say that the applied voltage, the applied voltage, the applied voltage. How much is the applied voltage? V. And 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 the resulting current, and the resulting current. How much is the resulting current?
V bar
I bar.
sir.
Current I bar. So the applied voltage and the resulting current are in phase, are in phase. Previously we usually seen these things, that see somewhere here. See, this is what the net voltage capital V and net current capital I. Between these some angle is there, see theta. Here also net voltage and this red color one look like current. So between current and voltage there is some angle theta. But whereas under resonance condition the angle has vanished. See here, total voltage is lying on the 0 degree line. This is what the 0 degree line. The current is also lying on the 0 degree line. The current and voltage both are lying on the 0 degree line. So this is what the current. So current and voltage both are on the 0 degree. That's why we are calling applied voltage and resulting current are in phase. Or in phase. In which condition? Under resonance condition. This is one of the important point. Okay. Next is second point is that so the net reactance, the net reactance, the net reactance. How much is the net reactance? X. We had seen that. Just let me show that here. Yeah, see here. This is what the net reactance, which is XL minus XC. Under resonance condition, XL is equal to XC. Then when XL is equal to XC, what is the net reactance? 0. So net reactance of the circuit is 0 at resonance since 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 XL is equal to XC. Right, because X is XL minus XC. So as both are same, so X net reactance is 0. Next third point is that the impedance of the circuit, the impedance of the circuit is Z is minimum. The impedance of the circuit is minimum. Why I am saying this as minimum? See that here we had seen somewhere. Yeah, see here. The impedance is usually square root of R square plus XL minus XC whole square. Under resonant condition, this term goes 0.
Yes, sir.
Means that is the minimum value of the impedance. Then other than that, if we add any value here, if some XL minus XC is existing, some value, whatever, negative, positive, whatever it may be. So if it is negative, negative square is again positive. So any value other than 0 of this term will contribute some value over here. Addition of any small value to this R will be higher than this R. That means at resonance condition, this is the minimum resistance. which is the minimum impedance of the circuit. So under resonance condition, the impedance of the circuit is minimum, which let me write as Z is equal to R. How much is that minimum? Is R. Is R. Okay. So next point. Let me take fourth point is that. So then this is regarding the frequency. So let us say the frequency, the frequency Fr is what the resonance frequency, which is equal to 1 by 2 pi square root LC. 1 by 2 pi square root LC. If you need the angular frequency, you can write omega r as 1 by square root LC. Okay. So what we need to do is that simple thing out of all these things. So first try to observe whenever you see the phenomena of the resonance. First try to find, let me take first get the circuit impedance. Circuit impedance. Total circuit impedance. Z. In the next step, if the circuit consists of active and passive elements, in the next step, so equate imaginary part of Z to 0. For what? For resonance condition. For resonance condition. Okay. In any circuit which consists of active and passive elements, so get the circuit impedance first, then equate the imaginary part of the impedance to 0. You will get the resonance condition. For example, let me show. For example, if it is the RLC circuit, RLC. If it is other than RLC circuit also, no issue. How much is this? Is R. This is ZL, which is equal to J omega L. This is ZC, which is equal to minus J by omega C. Now how much is the impedance? Let me get total impedance is equal to R plus J into omega L minus 1 by omega C. I got the total circuit impedance in this way. Now what is the imaginary part in this? Imaginary part is this portion. This is what the imaginary part. So in order to get the resonance, what we need to do? Im means imaginary part of the impedance must be equal to 0. For what? For resonance condition. For resonance. Then as a result of this, what is imaginary part here? Omega L minus 1 by omega C is equal to 0. Then just simplify this, you will get omega square is equal to 1 by LC and omega is equal to 1 by square root LC. And if you need the frequency, f is equal to 1 by 2 pi square root LC. These are what the resonance frequencies. Okay. So in this way, you can get in simple terms like all these points which I discussed about the characteristics of the resonance. In simple words, you can say that imaginary part of the impedance must be 0 at resonance condition. Thereby, the impedance will become pure resistor. See here. Once this imaginary part goes 0, what is the impedance? Only resistor. Okay. So this is what the resonance concept. So in a series RLC circuit. Okay.